morning. I am Rajesh, final year university student at IISc Bangalore, and this is a joint with Karthik, final year ME Telecom student here at IISc, and Professor Vinod Sharma from IISc. So we have carried out a performance analysis of data and voice connections in a cognitive radio network. Here is a quick outline of this presentation. We start off with a brief introduction to this topic. I will briefly describe the motivation for our work and the contribution of this paper. Then I will move on to describing the network model that we have used in this work, and then I will present the analysis that we have carried out for TCP traffic, pure TCP traffic, pure CDR traffic, and the mixed traffic when there are a mixture of CDR and TCP connections. And I will wind up with some conclusions and some of the future things some of the things that we are planning to do in the future. So quick introduction to cognitive radio networks. The motivation for cognitive radios comes from the need to achieve higher spectrum utilization. If you think about the current licensed wireless systems that have been deployed, they follow a fixed spectrum allocation policy, meaning spectrum bands, frequency bands are licensed to certain operators, and those operators are not permitted to use any other band even if they are free. And this fixed spectrum allocation has been shown to result in severe underutilization of the RF spectrum. So this cognitive radio software helps us in achieving higher spectrum utilization. How the concept is very simple. We already have the primary users in our network, the licensed users. The users were licensed to use the frequency bands available. Now we bring in another set of users whom we call the secondary users or cognitive users, and we let these users access and use the licensed spectrum dynamically, making sure that they don't interfere with the usage and the activities of the primary user. So we moved from a fixed spectrum allocation policy to a dynamic spectrum allocation policy, and this dynamic spectrum access can be done in a variety of fashions. The way we have used this work is vertical sharing by overlay. So when I say vertical sharing, I mean that the primary users have got preemptive priority over the secondary users. And when I say overlay, I mean that the secondary users access the channels only when they are not in use by the primary users. So that is the form of DSA that we have assumed in this work. One of the major functions in cognitive radio networks is spectrum allocation. So in a network, you'll be having a set of licensed channels, you'll be having a set of cognitive users who are waiting to use these channels when they are not being used by the primary users. And these cognitive users will be requesting for different kinds of connections. For example, they will be requesting for TCP connections or voice connections or video connections. And these connections, these different applications have got their own quality of service parameters. For example, for TCP connections, we consider the mean throughput as a good quality of service parameter. For voice connections, we are more concerned about the average end-to-end delay and so on. So these cognitive users are requesting for different kinds of connections, and they have their own quality of service parameters, and we need to allocate the licensed channels to them in a way to guarantee them a certain quality of service. So what we need to do is, in order to be able to do this, we need to have closed form expressions for these quality of service parameters that can tell us what would be the value, for example, of throughput that a cognitive user will get if I allocate a given license channel with its parameters to this user. So you need to have closed form expressions for these various applications, for the URL parameters of the various applications. So what we have done in this work is that we have considered two predominant forms of traffic. The TCP traffic is used for carrying most of the data in the and the CDR traffic is used to carry voice and real-time traffic. And what we have done is we have computed expressions for the throughput of this TCP connection. Remember, these are cognitive connections. These traffic are carried by the cognitive users. So they exist in the network in the presence of primary users who have got preemptive priority. So we compute expressions, approximate closed form expressions for the throughput for TCP connection and the average end-to-end delay for the CDR connection in a pure traffic as well as a mixed traffic scenario. So that is a quick summary of our work. The network model that we're using is we consider one primary channel, one licensed channel, and the model usage of this channel by an on or continuous process. So on refers to the duration duration when the channel is being used by the primary, and off refers to the duration when the channel is not being used by the primary and hence can be used by the secondary user, the cognitive user. And these on and off periods have a general IID distribution. And we follow a basic queue model in a network, meaning the primary traffic and the cognitive secondary traffic are organized in forms of queues. So there are two queues, the primary queue and the cognitive secondary queue. And the primary queue has preemptive priority over the CR queue, and they are accessing the same common license channel. So let lambda p denote the arrival rate of packets into this primary queue. Let S3 be the generic transmission time of the primary packet. We assume that the utilization factor of this queue is less than 1, meaning that there is some spare bandwidth available for use by the cognitive user. We assume accurate spectrum sensing, so we assume that there is some good sensing technology in place. And an observation from this model is that the queue-length process forms a regenerative process, meaning packets arriving into this primary queue see empty queues as a renewal process. So that's how it goes. So what we do next is this CR queue can be carrying TCP traffic or data traffic, and that can be one queue or more than one queue. So for each of these cases, we try to compute approximate closed form expressions for the quality of service parameters. So we'll start off with the TCP traffic. So we'll start off with one CR connection carrying TCP traffic, and we'll try to find throughput of. So that is the next topic. Throughput for a single TCP cognitive connection. So when I say TCP connection, it's the cognitive user which is carrying the TCP traffic. So again, let LP be the generic TCP packet, then let's see the capacity of the channel. So the mean service time of a TCP packet will be this. So note that we are using lowercase s for denoting the service time. We use reserve uppercase s for denoting the sojourn time. So the mean service time of a TCP packet will be given by this expression. Then we try to compute capital T subscript T, which is the time taken by TCP packet to complete service. So once its service has started, what is the time that it takes for the service to be completed? So it will take this service time, obviously, for the entire packet to be transmitted, plus while its service is in progress, if there are packets arriving in the primary queue, those packets will be served first because the primary has the preemptive priority. So this packet which has been transmitted partly has to wait until these primary packets that arrive after its service has started have been served. So what is the total time that this TCP packet has to wait because the primary packet that arrive after its service has started has to be transmitted? So this is the service completion time. So in this amount of time, the approximate number of packets that arrive in the primary queue is this. This is an approximation again. So this is when, as I said, these are approximate close. So we are using a MG1 kind of approximation for the primary queue. This is the number of packets that arrive in this duration TT, and each of these packets takes this much amount of time to be served. So this is the total amount of time that the TCP packet has to wait because some primary packets are arriving after its service has started. So using this equation, you can compute an expression for the expected value of CT, which is the service completion time. And then the next thing that we try to do is to find the mean sojourn time of the TCP packet in the queue. So this is the standard expression for the waiting time in a lower MG1 queue, and there is a higher priority MG1 queue already in the system. And this is the service completion time we computed in the previous slide. So this is an expression for the mean sojourn time. And once we have this, we can compute the throughput of the TCP connection, again an approximation using this formula, which will be something of this form. So in order to be able to compute this, we need to find out this expression, which is the stationary mean window size of the TCP packet. There are several approximations already available in literature for computing this. For example, people's law of ABCMC showing the various dates and the transition probability in terms of this packet loss probability Q. So there are approximations already available in literature for computing this, so we use one of them, and this can be computed. So this is an approximate closed form expression for the throughput when there is a single connection. When there are multiple connections, so there are multiple cognitive TCP connections, we assume that the packets are served in a first come first served basis. So since they are being served in XPSS fashion, you can think of all the packets as being part of a larger queue, a single large equivalent queue. And what we try to do is to find out parameters, expressions of the different parameters for that single large equivalent queue. So there are n TCP connections here in the network, and for the IISc connection, let's please see the notation. We are just adding a subscript I to denote the parameter for the IISc connection. And now we try to find out expressions of the different parameters for that one single equivalent queue, equivalent of this n TCP connection. So the overall stationary throughput that is obtained, which is the arrival rate, will be a summation of the individual lambda. And similarly, you can compute the equivalent parameters of these things. I will not go into the details of this, but this is the philosophy. We are trying to compute the parameters for that single equivalent queue. And then again, the mean source and time will have a similar form as before. So again, this is for that single equivalent queue. And then throughput of each of the connections can be computed within this expression. So we have n equations here, one for each connection, and this is another equation. So we have n plus 1 equation, and here n plus 1 variables. So these are unknown, all the n throughputs are unknown, and this is unknown. So we have n plus 1 unknown and n plus 1 equations, so we can solve these equations and compute the throughputs for each of the n TCP connections. So this was the multiple TCP analysis, and to validate, we have used a lot of approximation to validate the accuracy of our expressions. We carry out simulations on Qualnet network simulator. So we model the primary user traffic as having length which is uniformly distributed with some mean, and the arrival time. Again, there is no general distribution on the simulator, so we chose the parallel distribution which is available on the simulator with mean this, and we have chosen this values to ensure that the implementation factor of the primary is 0.3. So 70% of the time the channel is available for use by the cognitive users. And cognitive users, we have two TCP connections with some packet length and a maximum window size, and capacity is something. And so we simulate this scenario, and these are the throughputs that we obtain, and these are the theoretical throughputs that we calculate compared from the expressions that we have today, and we see a very close match. So our expressions are accurate. Next we move on. So this was for the case when we index Q equal to 0, that is packet loss probability is 0. For Q non-zero, again we carry out similar simulations, and again we see a close match in the simulated and the theoretical throughputs. Next, moving on to CDR traffic. So now what we have is we have one licensed channel as before, and now we have one or more CDR connections. So the cognitive users are carrying CDR traffic. And the quality of service parameter that we are interested in is the average end-to-end delay, which is the mean source and time plus the propagation delay. Again, we use MG1 approximation for the primary and CRP, and if these are the parameters, again we can write down a similar expression for the source and time of CDR packet. And when the propagation delay is added to this becomes the average end-to-end delay, and that is the expression for the quality of service parameter for pure CDR traffic. When there is a mixture of CDR and TCP traffic, for the mixed traffic case, what we do is, so now the scenario is we can have one primary license channel, and we have both TCP and CDR connections. So there are different CRQs, we may be requesting for CDR or TCP connections, and we give priority to CDR packets, which generally carry the real-time traffic. We can give priority to CDR packets over TCP packets. And again, we use a MG1 kind of approximation, and we can write down the quality of service parameter for CDR will remain the same as before because it has priority over TCP. So the addition of TCP doesn't affect its average end-to-end delay. So for CDR, the expression remains the same. But for TCP, the source and time will be different now because we have the effect of the CDR users as well, which have a higher priority than them. And so this is an expression for the mean source and time, and the overall throughput is this. And in a way similar to what we have done, we can find out again the throughputs of the individual TCP connections. So this is the throughput. This is the throughput of that overall, the combined equivalent TCP connections of all TCP connections which are here. And in a way similar to what we have done before, you can find out the individual throughputs. Yes.
When you're considering both TCP and CDR connections for cognitive radio systems, you have suppose the CDR service going on in the primary channel, not the TCP connection going on in the primary channel. So what is the priority that you
primary users always has
Always say
right?
that.
So that is the basic
Whether it
philosophy
is
of cognitive users.
non-real time or real time.
Yeah. Primary users always have preemptive priority. So if a primary user wants to transmit something, this cognitive users have to keep quiet.
Okay, and you are assuming that the total number of primary users remain fixed. Some of them may be moving into other regions or remain.
Yeah, so this is given the primary, so we have this channel whose on off period.
Dynamics of the scenario.
So we assume that we know the distributions of the primary traffic, the service time and the other things. So because that affects the way in which our license channel is used. The on-off model depends on how the primary users are using the channel. So we know that we have information about the primary traffic. Okay, so again, to validate the accuracy of these expressions, we carry out simulation. Primary user, we keep it the same as before. For the cognitive users, we put in one CDR connection and three TCP connections with these parameters. And again, simulated throughput turn out to be very close to the throughput that we get using our expressions. So this is a validation of our expressions. Again, so this was the case when we set Q equal to 0, there is no packet loss probability. And this is with some Q. So when there is some non-zero probability of packets or the RAM, so it needs to be access to loss. Again, match those. Some of major references. So what we have done is in this work we have considered one primary channel and obtained corresponding expressions for the throughput of cognitive TCP users and the average end-to-end delay of cognitive voice CDR users in a pure and mixed traffic scenario. And we have rectified the accuracy of our assumptions by Gaussian simulation. What can be done in the future is one thing is obviously to consider multiple license channels, which will be the case in practice. We can also carry out an analysis of video traffic, which is not part of this work. We can evaluate, try to compute expressions for the jitter of voice traffic, that is also able for video service parameters of voice. And in our work, I didn't mention this explicitly, but all the while I was assuming infinite buffer length for the CRQs, which means packets, as many number of packets as they come in can stay in the queue. But we can also consider the case where the buffer length is denied. So when the buffer is full, there is a probability that packets can be blocked as well. So for that case, the analysis will be first relative optimal connection to the
Time for one question.
So intermittent channel availability implies that TCP itself adapts infrequent channel availability for secondary users. Means that TCP itself will adapt its packet size and all other things. For example, if there is trivial traffic, then it will get very little chance to TCP traffic. So TCP needs to adapt it.
So one result that I did not mention is was part of Professor earlier work is that when there is a mixture of CDR and TCP traffic, if we give priority to the CDR user, we do not lose anything for the TCP connection. So something that we can say may sound magical, but that is what happens. We give priority to the CDR user, but then if you compare the throughput of the TCP connection with the lower end priority, you will not see any significant loss. So it's almost similar for me.
So in that case, even if the primary user is connecting TCP.
So TCP, we're looking for average TCP. So if you give priority to CDR, TCP will still get its average. So in that sense, so your question was TCP adapting?
Yes.
Adapting to what? So whenever the channel is available to it, something traffic at that time. Now, one thing that has been ignored is fragmentation of that. Now, that has been ignored here right now. That would be additional overhead which one needs to include in the control. But otherwise, they are
And you might also be meaning how the window size changes. So we follow the same TCP and Renault version is one way in which you change the window size. So all that remains the same. Use the TCP Renault model.
I'm sorry, I have to break, but they're running a little late, so there is one more question, but maybe you can be taking this break. So, thanks for